Imagine you have a molecule, a beautiful, complex scaffold of carbons, but right in the middle, there's an oxygen atom double bonded to a carbon, sitting there like an unwanted hitchhiker. In organic chemistry, this is a carbonyl group, the hallmark of ketones and aldehydes. Sometimes that oxygen is exactly what you need, but other times you want it gone. Not just moved, but completely erased, as if it were never there, leaving only a simple, saturated chain of carbons in its wake. This is the magic of the Clemmensen reduction. Let's look at the transformation. On the left, we have a ketone. On the right, the resulting alkane. Notice how that double-bonded oxygen has been completely swapped out for two hydrogen atoms. To make this happen, we need a specific, somewhat aggressive set of tools. A mixture of zinc and mercury, known as an amalgam, submerged in a bath of concentrated hydrochloric acid. But why the mercury? If we used pure zinc, the reaction with the acid would be so violent that the zinc would dissolve away into hydrogen gas before it could do much work on our molecule. By amalgamating the zinc with mercury, we create a more controlled surface. Think of it as tempering the zinc's enthusiasm, allowing it to provide a steady stream of electrons directly to our carbon atom. Let's visualize the mechanism, because this is where things get interesting. As we submerge our molecule in this acidic environment, the oxygen atom is immediately drawn to the abundance of protons. It grabs one, becoming protonated. This makes the carbon it's attached to feel quite electron deficient and vulnerable. Now, watch what happens at the surface of the zinc. The zinc atoms donate electrons to that thirsty carbon. As the carbon gains electrons, the bond with the oxygen weakens until, eventually, the oxygen is kicked off entirely, departing as a harmless molecule of water. At this point, our carbon is left with a negative charge, a carbanion. But it doesn't stay that way for long. In this sea of acid, it quickly grabs protons to fill the void. Repeat this dance one more time, and that original carbonyl carbon is now bonded to two fresh hydrogens. The oxygen is gone. The transformation is complete. But there's a catch. Because this reaction happens in a literal vat of concentrated acid, it's not for everyone. Picture a molecule that has other sensitive groups on it, maybe an ester or an alcohol. If we drop that into the Clemmensen acid bath, the whole molecule might fall apart or react in ways we didn't intend. This is the central challenge of organic synthesis, choosing the right tool for the job. If your molecule can't stand the heat of the acid, you might look toward its brother reaction, the Wolff-Kishner reduction, which does the same job but in a basic environment. So, the next time you see a ketone and wish it were a simple alkane, remember the Clemmensen reduction. It's a reminder that in chemistry, as in life, sometimes the only way to move forward is to strip things down to their simplest parts. Provided, of course, you can handle the acid.